So now we will do the sizing, right? So I just want to remind you again what we discussed last time, right? We say that for last time, right, this is equivalent capacitance, right? So from now on, we call our equivalent P and equivalent N represents the minimum size device that you can draw in the technology, okay? And last time we say that R equals to R equivalent P divided by R equivalent N. And this one is related to the saturation velocity of N divided by the saturation velocity of P. Just a reminder, this is the last slide we did last time. Is this okay? My internet had problem. Let me repeat one more time. Last time in the last slide, right, we talked about the ratio, which is R equivalent P divided by R equivalent N. These are talking about the minimum size device, okay? Their resistance ratio, let me write it very clearly, is R, not gamma, right? The resistance ratio is just equal to the saturation velocity of N divided by the saturation velocity of P. Right? So what is the takeaway? It's just that, yeah, if you lay out PMOS and NMOS of the same size, they don't have the same resistance. I think you are okay with that. And what is their ratio? It is R. Okay. Now, I also want to revisit the idea one more time about the VM, right? So at that time, we did not really study what is the W on L ratio of P and N that will give, right? The question is what W on L P divided by W on L N will give Vm equal to VDD divided by 2. What value can we choose so that it will give this one, right? The rest is just derivation. But I hope that now you know what is Vm, right? Anyone tell me what's Vm?
Vm is when V out equals V in.
Yeah, very good, right? So if you have different sizing, you can have different VTC, right? And this is the Vm curve. This is V in equal to V out. Okay, if this is VDD, then this one maybe give you VDD divided by 2. Not all of them will give you VDD divided by 2. This one is also Vm. This, let me just use laser point. This one is also Vm, but this Vm is not VDD divided by 2. Okay, so how should we size it so we can get Vm equal to VDD divided by 2? We just use this equation, right? So we say, let me just use this equation. It means that I need to have Kn dash Vd set n, right? But now Vm, we want it to be VDD divided by 2, right? Because that's what we said, minus Vtn minus Vd set n divided by 2 divided by Kp dash Vd set p times Vdd minus Vdd divided by 2, because Vm is Vdd divided by 2 by definition. Vtp plus Vd set p divided by 2. Okay. Now I assume Vdd is much larger than Vt and also much larger than Vd set. So then what will happen? When it is
VD or VB?
VDD. What VB? VDD.
Is that VD or VB sat?
Sorry, VD set. VD set. Okay. So if VDD larger than VTH, so this one is gone, right? Maybe I use another color. Because it's larger, right? So it is gone. VDD larger than VD set is gone. This is gone, this is gone, right? A lot of simplification, I know. Then it becomes VD set N times VDD divided by 2. And the bottom is also VDD divided by 2. Right? So this is just Kn dash VD set N divided by Kp dash VD set P. Is this okay so far?
So is this the curve up that you drew at the top? Is that for a single inverter, or is that inverter cascaded with another inverter?
This is about VM, right? VM doesn't matter if you have loading or not, because this is not a transient simulation. VTC is like, we don't care about the capacitance at this point, right? VM does not depend on the loading. Remember? We switch it very slowly, okay? Yeah, so doesn't matter if it's cascade or not. Okay, but here again, we use the equation we learned before. VD set N is just not equal to Vn times velocity, saturation velocity of N, right? So this one equals to Kn dash Ln saturation velocity of N divided by Kp dash Lp saturation velocity of P. I think I'm wrong. Should be what? Sorry, this should be
W over.
This one should be critical, right? The critical with electric field. Right, the critical electric field times the channel length give you the saturation velocity. Okay, but Wn over Wp is just equal to mu n C ox Ln E, right? Mu P C ox Lp E critical P, right? So the C ox got cancelled, and then mobility times the critical electric field give you the saturation velocity, right? Here I'm also going to cancel this Ln and Lp. We will say Ln equal to Lp. Assume minimum gate length. When you lay out any device, usually you use minimum gate length. You can change the width, but usually for P and N, you always use the minimum one.
So this is what I was going to ask about the VSAT N over VSAT P ratio. That's going to be different when you attach a second inverter for the same VDD. The W is going to be different to get the same VM. You know what I mean?
It would not. What? For example, you are talking about this, right? This is the stage we're talking about. And now when you attach a new inverter, it's not going to affect this VTC.
But I mean, you're going to need a different PMOS width. Is that correct? To get the same VTC.
But it has nothing to do with this inverter, because this inverter draw no current.
Okay.
So our conclusion here is that if I want to have the same VM, right? To get VM equal to VDD divided by 2, then I need W on LP divided by W on LN equals to R. You need to set it equals to R.
Professor,
Uh-huh.
the Kn value, Kn dash and Knp, is it technology dependent?
Very good, right? What is Kn? Is mu n times Cox, right? Cox is technology dependent, right? Because it's the gate oxide capacitance. Mobility also technology dependence because in the old time maybe not much, but actually it also does because it's the mobility, it depends on doping. But nowadays for 45, 65, 32, even FinFET, they do a lot of thing called string effect. They string the silicon so that enhance the mobility.
Okay.
Yeah.
Okay. Thank you.
Sure. So that's a good question. That it means if I ask you to use 45 nanometer technology, your R will be different from 40 nanometer technology FinFET. Right? If you want to get the same VM, you need to size them accordingly. But of course, here this what they're all approximation. We did a lot of approximation. It might not work actually. I tried that for FinFET. Because they are very different now, because we cannot say VDD is much larger than VT, right? But you have this insight and then use spice simulation to help you to simulate. Now, one approach I will do is, let me just start with large VDD. And then do I see really what I learned in my class, in my theory? If I do, then I know that all my simulations set up are correct. Then I just reduce the VDD and then start optimizing it. In your homework, you also see that this is not exactly the case. Okay. Now, a lot of math really doesn't matter. Again, I'm not going to ask you to derive this math in the exam, right? Even I don't think anyone will ask you to do this in interview. But the point is, you should have the insight to see that, hey, to get VM, I want the ratio to be the ratio of the width of the device, the width ratio to be the R, which is the resistance ratios of the minimum device. That makes sense. Actually, after all, I'm just telling you something trivial. If the NMOS, if the PMOS is more resistive than NMOS for the same size, you need to make it wider so that they will have similar resistivity so that your VM is VDD over 2. Okay. Now with this basic knowledge, then we are going to use it very soon. We try to size for minimal delay, right? To find the minimum delay for inverter train, what we need to do is first come up with the correct equation. Okay. So first, let's say what is the loading, right? Let me write it again. Remember, this is the driver, right? My goal is to find the delay we are interested in is from V in to V out, okay? And this is the load. That is the scenario. And we say, what is the loading? Well, we say that this is, I'm not going to write in this language. I write the language I told you earlier, C dN1 plus C dP CDP1, right? The first stage capacitance plus the wire capacitance comes CGP2 plus CGN2, right? Which means second stage gate PMOS capacitance. Okay. Now, if let's say you do some sizing, right? You find that W on L of PMOS divided by W on L of NMOS equal to beta. This is not, we're talking about the sizing, the ratio, right? What do I mean? For example, let's say your M2, which is PMOS, this is M2, right? is equals to 44 nanometer divided by 22 nanometer. The width is 44 nanometer. The length is 22 nanometer. And M1 equal to 22 nanometer by 22 nanometer. What is beta in this case? Can someone tell me what is the beta? Right, this is P. This is N. What is beta?
2.
2. Right? Very simple, but we need to really know what we are talking about, right? For example, this is just example. Okay. If the PMOS has is beta times wider than the NMOS, let's also assume Ln equal to Lp, which we mentioned earlier, right? Just minimum size. Right, we try to save the area of the transistor, right? For length, we all make them the same size. Then we're going to make the width wider, right? Then it means WP divided by WN equal to beta, right? Let's say 2 times larger. For example, in this case, minimum size 22 nanometer gate length, but the width of M2 is 2 times wider, right? What happened to the capacitance CDP1 to CDN1?
Should be 2 times bigger, right?
2 times. Why? See it here, just example, right? You mean beta times wider.
Beta time, yeah, beta time drain capacitance is going to increase as the W increases.
Exactly. And that's why I keep emphasizing, if you forgot at here, right? I say that you look at this CDB, CG1, they all proportional to beta, to width, I mean, right? To W. So now I tell you that the top one is wider than the bottom one by the PMOS wider than the NMOS by beta. Then of course, the capacitance is beta times wider, right? And let me do the same thing also for the second stage. Then naturally, I have CGP2 equals to beta times CGN2. Okay, that is the first thing, right? So CL, because of this, becomes C, how should I put? Let me just put everything. Beta CDN1, this is for CDP, plus CDN1, right? Plus W, not W, I say it wrong, should be CW, right? The wire capacitance, plus beta CGN2 plus CGN2. Okay, so you do some manipulation, it becomes beta plus 1 times CDN1 plus CGN2 plus CY. Right, so now by introducing beta, I got an expression about how this loading is going to be. Any questions? I'm not there yet, right? You might forget the equation, but just hopefully in this process, you remember that we play with beta. We simplify it a little bit. Okay. And this one I need to skip. At that time, I thought I need more space. Right. So here shows something interesting. Okay. Now, let me make sure. I want to make sure I'm using the correct stats. Okay. Yeah. Okay. Now, so when you do beta, which is WP divided by N, let's sorry, my connection was not good. So when you do beta, right, which is WP divided by N, okay, then look at the propagation. I also asked you to do in the assignment. What is the minimum propagation here? It is at this point, right? It is a excuse me, let me take a quick look on my cheat sheet. I need to make sure that I did not miss anything. Sorry for that. Yeah, sorry, I did something wrong. Just hold on. Here I try to show you that is that when the beta, when you want to have the minimum delay, you have your beta is here. But if you want to have a symmetric VM, this is a VM equal to VDD, you have different beta. Okay, but I skip a little bit. So I'm sorry, I got messed up on my flow. Let me say one more time, right? We try to size for the minimum delay. Is that okay? And then we come up with CL equal to this. Okay. Now, what is the delay of an inverter? TP equals to TPHL plus TPLH divided by 2, right? TPHL is what? Can someone tell me what is TPHL? Or just the simple model? I'm asking the simple thing. How do you find the delay?
VOH minus VIL.
I'm asking for the delay, not the noise margin.
Is it
maybe
delta Q?
RC.
Say again.
0.69
Very
RC.
good. Very good. Yeah.
Sorry, I don't know why I blinked out there.
Yeah. So I will say R from high to low plus R from low to high times C low divided by 2, right? But what is R from high to low? It's through the resistor, right, of MOS. Okay, but this is the minimum size. Remember, this is the minimum size. We are making the MOS minimum size. But how about the R from L to H? This is the PMOS resistance, right? But we are not using minimum size. What do we use? We make it beta times larger, right? So it is going to be divided by beta, the resistance. For example, right, remember that we make it 44 nanometer by 22 nanometer. So this is equal to the resistance of 22 nanometer by 22 nanometer PMOS divided by 2. Right, you make it wider, so your resistance is smaller. And of course, we need to remind ourselves the so-called R EQP divided by R EQN equals to R. This is the minimum size, right? At the beginning, I told you the ratio of the resistance of P minimum size PMOS to NMOS is R. Remember that? Minimum size, right? For example, this can be 22 nanometer by 22 nanometer. This is also 22 nanometer by 22 nanometer. NMOS and PMOS, they already have different resistance. Now in my inverter, I size it so that the PMOS is 2 times larger, beta times, which is 2, for example, larger. As a result, the resistance is going to be beta times smaller, right? Is this okay? A little bit confusing, but is every step okay? Yeah, you should ask now if there's anything not clear, right? Why go back to learn? Understand it now. So I assume you're okay then. What is TP? TP equal 0.69 divided by 2. I have CL, right? But this time I'm going to say RHL, the NMOS, because it's a minimal size, so it's R equivalent N. However, the PMOS is R equivalent N divided R equivalent P divided by beta. And then the whole thing times CL. I mean, I already have CL, sorry. Now, then what is CL? What is CL? We already proved here. CL is beta plus 1 times this whole term. Okay, so I'm just going to copy beta plus 1 times C DN1 plus CG N2, right? Plus CW. This is CL for the whole thing, right? And at the same time, I already told you that the R equivalent, maybe I'll use another color so that when you study, you'll be easier. This R equivalent is just equal to R times R equivalent N. R equivalent P is just equal to R times R equivalent N, right? So the whole thing I becomes 0.69, 0.345. That's one thing. And then I can take out this R equivalent N times 1 plus R divided by beta. What I'm playing is this one. I take out R equivalent N. And then this becomes 1 plus R divided by beta for this one, right? And then this part becomes beta plus 1 times CDN1 plus CGN2 plus CW. Is this okay? Is this so far okay for the flow? Let's take a 1 minute break, right? Ask question if you have. So I assume you're okay, but basically what we are doing is the difficult part is that you need to remember we are doing minimum size NMOS, and then we scale PMOS. And then we use this minimum size relationship of R and also this beta to simplify the equation, right? So what is the minimum delay that we can do when we size? How should we size our beta so the delay is minimum? Right? Why we need to ask this question? This comes to intrinsic and extrinsic capacitance. You see the delay depends on beta. If my beta is large, the delay is large due to this term. This is because of the minimum size, the intrinsic capacitance. And you increase the capacitance by increasing beta. But at the same time, delay is reduced if I increase beta because I reduce the resistance, right? So what is the best value? What you need to do is do partial TP, partial beta, 0, set it, right? But I'm not going to solve it. Our goal is not math. Then you will find this. Beta equals to square root R, not R, times 1 plus CW divided by CDN1 plus CGN2, right? It minimizes TP, right? So if you can size your beta in this way, your inverter has the smallest delay, right? If CW equals 0 means we ignore the wire capacitance. Then beta equal to square root R. This one give you the minimal delay. Beta need to equal to square root R. Okay, recall, what did we say just now? If beta equal to R, right, we get Vm equal to VDD over 2, symmetric VTC. But if you want to have the minimal delay, you need beta equal to square root R. Okay, so for example, right, if the R equivalent, let's say the R equivalent of N is the R of NMOS equals to 22 nanometer by 22 nanometer. This is the minimum size. And let's say R equivalent P is the R of PMOS, also 22 nanometer by 22 nanometer, right? Because this is minimum size device. Okay, and let's say the V set P equals to 0.5 E7. V set N equals to 1 E7. What is R? Can someone tell me what is R by what we have learned? Let me show you the figure one more time. R equal to minimum size device resistant, PMOS resistant divided by NMOS resistant, which is V set N divided by V set P. So can you tell me what is the R in this case? R is V set N divided by V set P. Let me write it down, right? So what is R in this case? Can you hear me? No idea what is V set N divided by V set P? Anyone help me?
0.5.
Okay, good. What is V set N divided by V set P?
Root 2.
2, yeah. 0.5 is almost right, but you swap the sign, right? So because of this, to get symmetric VCC, how should I size the PMOS? We need beta equal to what? What should be the beta if I want to get symmetric VTC?
Equal to R.
Which is
2.
So what should be the size of PMOS? Can you
Double than the NMOS.
double that? So can you give me the absolute value?
2 times the NMOS.
2 times the M. So what is that? NMOS is 22 by 22.
Oh, 44 by 22.
Yes. Good. Right? But if I want to minimize the delay, I need a beta equal to square root R, which is about 1.4. Okay? So you will find that Now this is should be PMOS. WP over WP over WL equals to about 30 nanometer divided by 22 nanometer. Okay, is this okay? Any questions?
So the sizing concept basically starts with getting symmetric VTC first, and then getting the beta, and then figuring out the minimum delay.
Depends on your purpose. You cannot fulfill of them at the same time. You either have symmetric VTC or minimum delay. So the concept is that if you want to have minimum delay, you use square root of R, which is not symmetric. If you want to have a symmetric one, then you won't get a minimum delay. Okay.
Professor, what's the point of getting a symmetric VTC? Why do we need that?
Yeah, can you tell me again? I mentioned a few times. Symmetric VTC, what's so special about having a symmetric VTC? Can you try to recall? What's so symmetric? What's so special about symmetric VTC?
VM is going to be equal to V out equals to V in.
No,
VM is equal to VDD over 2?
Yes, VM VDD over 2, right? So VM, so it's just saying this, right? I'm going to erase it not to confuse you later. It's just saying that if this is VDD, this is VDD, symmetric VTC is like this, non-symmetric VTC is like this. From this graph, why this is better in certain cases?
In terms of the performance or power?
We talk about performance, we talk about powers. What else do we talk about?
Area and cost.
Okay, that is PPAC. Yes, but still something very important that we talk about, which actually reflected in the whether your circuit is going to function or not.
The delay.
Noise margin?
Noise margin, yeah, noise margin.
Oh, okay,
Yeah.
okay.
So here you have very small noise margin, right? So in some application, you want to have symmetric, but not always the best with symmetric VTC that will give you the best noise margin.
Okay, got it.
Okay, good, yeah. So I don't answer you right away because if we keep thinking about it, then you will get used to it, right? Now, so this one, I just had a problem somehow. I got lost in my cheat sheet, right? So here to show you again, the TP, you size it with beta equal to square root R, you get minimum delay. Here you size it with beta equal R, you get symmetric delay, symmetric VTC, right? Because the delay are the same. Okay. Now, so we are done with the first optimization.